Hello everyone. In this experiment, we will study the characteristics of the Geiger counter tube and the attenuation of radiation. In the first section, we will study the property of the Geiger counter tube to determine the operating voltage of the tube. The Geiger counter tube is the device that we can measure the radiation. In the Geiger counter tube, it consists of the wire with positive voltage and the cylinder wall with negative voltage. And in this tube, it's filled with an inert gas. And in nature, there are several radioactive elements that can radiate with different types of radiation such as alpha radiation, beta radiation, or gamma radiation. When the radiation enters the Geiger counter tube, it can ionize the gas molecules and produce chain reaction. The electrons and ions will be attracted to the electrode and produce the signal in the Geiger counter tube. And to operate the Geiger counter tube, we have to apply the voltage into the tube. If we operate the Geiger counter tube with low voltage, the energy is not enough to detect the radiation. So we cannot get any signal from this radiation. But if the applied voltage is too high, the gas in the Geiger counter tube will break down without any radiation. So this causes the fault detection. This means to operate the Geiger counter, we have to find the optimal value of the operating voltage of the Geiger counter tube. To determine the optimal value, we will adjust the voltage of the tube and detect the count rate of the tube. When we plot the graph of the count rate and the applied voltage, we will see the characteristic of the Geiger counter tube. It looks like a step voltage. At low voltage, no counts are detected because the energy is not enough. The electrons and ions in the tube cannot move to the electrode. As the voltage is increases, the Geiger counter tube begins to detect the radiation signal. The voltage at which the Geiger tube begins to count is called the starting potential or starting voltage. The count rate quickly raises as the voltage is increases. In this interval, the count rate depends on the applied voltage, so we cannot use this voltage in this interval. After a quick raise, the count rate remains constant over a certain region. This range of applied voltage is called the plateau region. When the applied voltage becomes too high, the continuous discharge of the gas will take place in the tube, and the count rate increases rapidly. To operate the Geiger counter tube, we will use the applied voltage in the plateau region to operate the Geiger tube. In order to find the optimal operating voltage, we will determine the threshold voltage, or V1, which is the point where the partial region begins. And another point is the maximum voltage, or V2, which is the point where the partial region ends. The technique that we use to determine these 2 points is drawing the straight line over the partial region. We can use the ends of the partial region from this line to determine the voltage V1 and V2. And then we can use this value of V1 and V2 to calculate the optimal operating voltage for the Geiger tube by using this formula. We use V1 plus 1 over 3 of V2 minus V1. And next I will show the experiment for the section 1. Okay, for this experiment, this instrument is for the experiment A. This is the Geiger tube to measure the radiation, and this is the counter to count the signal from the radiation. And there are a lot of switches on the counter. The first one is the cause adjustment, and this one is fine adjustment. And for this set of switches, this is to turn on and off the counter. The next one is the test. So we don't use this for this experiment. And this one is for counting the signal. We use it to count the radiation signal. When the counter finishes the process, the stops will become active. You will see the light is on. And the last one is for the reset the count rate from the counter. And for this one, this switch is the count time. We can set the time to measure the radiation. In the first section, we will set this count time to 1 minute. And in this experiment, the radioactive element that we use is strontium-90. This element decays by beta radiation. This is the radioactive element, so try not to touch it with your hand. We will use this forceps to hold this radioactive element and put it in the first socket. Then we adjust the applied voltage according to the table of the experiment. First, we will apply the 100 volt to the Geiger counter tube, so we will turn the cause adjustment to 0 and turn the phi adjustment to 100 volt. And then we press the count to measure the radiation. Then we just wait for 1 minute. Okay, after 1 minute, you will see the stop is active. Now the count rate is 0 because we apply the low voltage to the tube. Then we will apply the next voltage, which is 200 volt. So we turn phi adjustment to 0 and turn the cause adjustment to 200 volt. And then we press reset and press count to measure the radiation and wait for 1 more minute. Then we just repeat the experiment by increasing the applied voltage and recording the curve rate. Then we plot the graph of the curve rate and the applied voltage to determine the optimal operating voltage. Okay, for the section 2, we will study the attenuation of the radiation. When the radiation I0, this is the initial intensity of the radiation, travels through the material of the thickness x, the material will partially absorb energy of the radiation, and this radiation will be attenuated. So we can calculate the attenuation by using Beer-Lambert's law, which is I equal to I0 times e to the power of mu x. And the mu is the attenuation coefficient in unit of 1 over centimeter, and the x is the thickness of the material in unit of centimeter. In this experiment, we will determine the value of the attenuation coefficient of the material. However, this relation is complicated, which we don't like this one. So we will change this form into the linear relation. The way that we can change the form, we will apply the natural logarithm to this relation. So we will get log of I, and in the opposite side we will get log I0 and minus mu x. And if we compare this relation to the linear relation, the log I corresponds to the y variable, and the minus mu corresponds to the slope of the graph, and the thickness corresponds to the x variable, and the last term corresponds to the y-intercept of the graph. And in this section, we will measure the intensity of the radiation and the thickness of the material, and plot the graph of the thickness and log of the intensity subtract with the background radiation. We subtract the intensity with the background radiation because we need the result of the radiation from strontium-90 only. When we draw the graph, so we can determine the value of log of I0 and the value of I0 from the y-intercept. And another one that we can calculate from the graph is the slope. And from this slope, we can determine the attenuation coefficient with the minus of the slope in the unit of 1 over centimeter. And the last one that we have to determine is the half value thickness of the material. The meaning of this quantity is that this is the thickness that the material can attenuate the radiation by half. And we can determine this value by using the log2, the natural log2 over the mu, or the attenuation coefficient. The value of the attenuation coefficient comes from the slope of the graph, and this value is the characteristic of the material to absorb or attenuate the radiation. And before we measure the radiation, we have to measure the background radiation. So in the section 2, we will measure background radiation first. So in this experiment, in the section 2, we will measure background radiation, which comes from the environment around us. We remove the radioactive element from the tube, and apply the operating voltage from the section 1. So for me, I get the operating voltage is the 670 voltage. Then I will turn the cross adjustment to 600 volt, and I turn the fine adjustment to the 70 volt. And then we will set the count time to 5 minutes in this section. And then press reset and count the radiation. And then we just wait for 5 minutes. So when we get the background count, we will measure the attenuation of the material by putting the strontium 90 in the fourth socket from the top. Then we will use the material for the attenuation. In this one is a polymer. So we will put this material in the third socket from the top. And the thickness of this material is 0.01 centimeter. And then we set count time to 1 minute with the same operating voltage. Then we press reset and count the radiation. And then we just wait for 1 minute. Okay, after 1 minute, we will change the thickness of the material according to the table of the experiment and record the result. Then we will subtract the count rate with the background radiation and plot the graph of the log of intensity minus the background and the thickness, and then we determine the y-intercept and the slope from the graph. Now you can see when the counter finish measurement, the stop switch will be active. Then you can continue on the different thickness, and don't forget to press the reset.